So I'll try and set the stage a little bit for our discussion today. I know, I mean, the topic is pretty heavy, design, disruptive technologies, and all of that. And it's been talked about so much that, that we talk about additive manufacturing, IoT, big data. The idea here is to look at a few of these disruptive technologies. I have a very broad set of colleagues with a broad set of background here, so hopefully they'll be able to bring a lot of perspective. I'll bring in my own. I have Pradeep Nair, who is the Managing Director of Autodesk in India. Is the CTO for software systems, connected MCUs, and embedded processing at Texas Instruments. And Vinay, who is the MD of Infineon Technologies in India. In Vinay's role, he's responsible for the growth of the business, marketing, and R&D. All these operations report to him in India. I talked about one technology, autonomous vehicles. How's it for you?
Two things. One, autonomous driving. I think it's a buzzword nowadays. After IoT, it's autonomous. But we combine autonomous with electric vehicle. So my context is the combination of electric vehicle and autonomous driving. Now, the combination of the two create disruptions on multiple fronts. Number one, societal. Did you know that 1.2 million people die of road accidents every year? Now, this is more than one Boeing fully loaded falling from the sky every day. And no one even talks about the impact of 1.2 million people dying. Electric vehicles, so autonomous vehicles are seen to be a panacea for the accidents and the deaths that occur. So that's a societal impact. Second, look at the amount of petroleum and minerals that we are just pumping out of the earth. With electric vehicles, that is bound to go down significantly. So I think these are the two disruptions on the societal front. Let's look at the industrial front. You're talking about internal combustion engines that have been surviving 160 years. It's amazing that they survive 160 years. Will probably go very, very quickly. That's one. Autonomous driving increases safety. But on the industrial front, I would say the disruption is in opening up of the entire value chain. If you see conventionally, the automotive industry has OEMs, which are car manufacturers or vehicle manufacturers. They buy from the tier ones, whether it's your metal, plastics, electrical harnesses, electronic ECUs, as we call it, electronic control units. So these are bought from the next tier of the value chain called the tier ones. And then behind them are the tier twos, typically semicon companies or component suppliers. So for such a large industry, it's a very short value chain, and it's a very closed value chain, and not because of any other political reasons or lobbying. It's primarily because of the reliability required in this industry is so high that unless you have a strong track record, it's very difficult to get into that industry, whether you're an intermediary or you're a component supplier. It's easy to come in as an OEM, as a car manufacturer, but it's a lot more difficult and almost impossible to come in as a tier one, and more so as tier two, which is again an inverted pyramid in some senses. So the system integrators can be many. That's why you see so many automotive makers in China who came out of nowhere. But on semiconductors and in tier ones, it's still the Bosches, the Continentals, the Delphis. There are just about 6-7 companies that rule the world. Now with electrical, it's no longer internal combustion engine. It's about the motor. How do you control the motor? How do you charge your battery? How do you discharge your battery? How do you do regeneration of power back from motion back to electrical? Now this is an absolutely new industry, and that's why companies like Tesla out of nowhere can suddenly start disrupting and start leading the disruption in the EV industry. And Tesla does not just, as an example, not just EV, but it combines autonomous driving with EV, which is where the big disruption will come. And any competitive advantage that the conventional automotive value chain had is now lost. And that allows tremendous number of new players to get in, building on what is already there today. What is there from a autonomous driving perspective, I won't talk about EV much. You need radar. You have 24 gigahertz radar and 77 gigahertz radar to sense short range as well as long range objects. You have cameras for a 360-degree view of a German car. If you take a Mercedes S-Class, you get a 360-degree view just through cameras, which is integrated on your dash panel. It needs 7 cameras to get a 360-degree view. So 7 cameras, 12 to 17 radars, 77, 24 gigahertz, ultrasonic sensors, And now for autonomous, you have to go into LiDAR, laser-based detection and ranging. Now, if you add up the total electronic cost that goes into autonomous driving today, it's more than $200,000. While technologically feasible as you're driving around in California, it's impractical for anyone to buy. If electronic itself costs $200,000, is it mass market product today? Definitely not. So scaling also is a very important factor. And you talked about power. The power consumption in today's autonomous cars that are running as a pilot is humongous.
That we see happening a lot.
A couple of other things that I would like to mention for those that are looking to get into this exciting space. One, like the aerospace industry, automotive is driven by what is called as functional safety and reliability. The level of reliability has to be extremely high because you cannot afford a failure, especially as you move towards autonomous. It's already there in the industry today. It's called ASIL, which is an automotive safety and integrity. And there are multiple levels that you have to achieve, whether you're handling the braking system or the body or the engine. So for autonomous, the highest level of safety and integrity levels have to be reached, whether you develop hardware, software, or systems. Now, and then there are, of course, standards that are derived from the aerospace, which are called ISO 26262. Now, together, to even fulfill these requirements of safety, the experience, my personal experience is that it adds easily 40% more cost to a deliverable. None of this comes free. So there's a huge difference between an industrial solution and an automotive solution, whether you talk about hardware or software or systems. So be aware, and this capability of functional safety and integrity is not just about following a process and having documentation, which is the concept that most of us have, but it also requires engineering, very creative technical solutions to create redundancy and isolation across, let's say, two different ways of computing the same a set of inputs and arriving and then matching them. So that complexity, technical complexity also gets high, which is on top of the function that you are developing. This should not be underestimated. So most of the semiconductor industry, including us, we are at level 2 going towards level 3. There is tremendous amount of data crunching, which is dedicated to computer vision. I think that is that evolution in terms of engineering capability, skills, talent, and looking, and we cannot do this vertically. We have to be dependent on the ecosystem. I think that's a change that Infineon as a company is going through.
Okay. Is there a photograph somebody?
Yeah.